Ever wondered how Java applications communicate across different JVMs? Well, that's where the magic of Remote Method Invocation, or RMI, comes into play. RMI is a mechanism in Java that's akin to a long-distance telephone call between objects. It allows an object residing in one Java virtual machine, JVM, to invoke methods on an object running in another JVM. The intriguing part? These JVMs can potentially be on entirely different hosts. This ability is a cornerstone of distributed computing, enabling the creation of networked applications that are distributed across multiple systems. Imagine a team of workers spread across different locations, each with their unique skills and capabilities, working together to achieve a common goal. That's essentially what RMI enables in the realm of Java applications. It brings together different objects, each running in their own JVMs, to work in unison, despite being physically apart. Now, you may ask, how does this remote invocation work? The answer lies in the concept of remote objects. A remote object is an object whose methods can be invoked from a different JVM. To be eligible for this long-distance interaction, a Java object must implement a special interface known as java.rmi.Remote. This interface is like a badge, signaling that its methods can be called remotely. But how do these remote objects find each other? To facilitate this, RMI uses a server-side naming service known as the RMI registry. This registry is where remote objects are registered and can be looked up by name, much like a telephone directory. The communication between the client and server in RMI is facilitated by stubs and skeletons. The stub acts as a client-side proxy for the remote object, while the skeleton serves as the server-side dispatcher. Together, they ensure smooth communication between the client and server. However, like any form of communication, RMI isn't immune to errors. Network communication involves various potential pitfalls, and to handle these, all methods in a remote interface must throw remote exception. So RMI is the mechanism that brings objects across JVMs to life, allowing them to interact with each other as if they were in the same memory space. What makes an object eligible for remote invocation? Well, in the world of Java programming, we have a concept known as remote objects. A remote object is an object whose methods can be invoked from a different Java virtual machine, or JVM for short. Now, you might be wondering how an object becomes eligible for such a unique form of interaction. The answer lies in the java.rmi.Remote interface. The java.rmi.Remote interface is a marker interface that serves a crucial role in designating an object as remote. It's like a badge that an object wears, telling the world, hey, you can call my methods from a different JVM. By implementing this interface, an object is essentially signing up for remote invocation. For instance, let's consider an example where we have an interface, myRemote_interface. When myRemote_interface extends the remote interface, it's an indication that the methods within it can be invoked remotely. It's as simple as that. However, it's important to remember that the remote interface doesn't contain any methods of its own. It's primarily a signaling mechanism that declares an object's willingness to have its methods called from a different JVM. Now, you might be wondering why we need such a mechanism. The reason is that remote method invocations come with their own set of complexities and potential errors. Therefore, it's necessary to explicitly mark objects that are prepared to handle these intricacies. So when you're designing your Java programs and you need an object's methods to be accessible from a different JVM, remember to implement the java.rmi.Remote interface. It's the key to unlocking the powerful feature of remote invocation in distributed computing. In essence, any object implementing the remote interface can have its methods called from a different JVM. And that, my friends, is the magic of remote objects in Java's remote method invocation. Ever wondered where remote objects reside and how they are accessed? Well, let's unravel the RMI registry. This is essentially a server-side naming service, allowing clients to look up remote objects by name. Think of it as a telephone directory, but for remote objects. Now, for a remote object to be accessible to clients, it must be registered in the RMI registry. This is akin to listing your number in the telephone directory. For instance, a registry might be created on port 1099, which is the default RMI port, and a remote object could be registered with the name myRemoteObject. So, when a client needs to access a remote object, it looks it up in the RMI registry. The registry points the client to the right location, and voila, the remote method can be invoked, just like how you dial a number from the directory. So, the RMI registry is the directory of our remote objects, enabling clients to find and use them. How does the communication between the client and the remote object happen? This question brings us to two pivotal elements in remote method invocation: stubs and skeletons. They are the unsung heroes of the RMI world, operating behind the scenes to make the magic of remote method invocation possible. Let's start with stubs. A stub is essentially a client-side proxy for the remote object. Think of it as an ambassador, representing the remote object on the client side. When a client wants to call a method on a remote object, it doesn't do so directly. Instead, it makes the call on the stub. The stub then takes up the task of sending this request across the network to the server where the actual remote object resides. It's the stub's duty to ensure that the request reaches its destination. Now, once the request reaches the server side, it's the skeleton's turn to join the action. The skeleton, much like its biological counterpart, provides structure, but in this case it's for the server-side dispatch process. The skeleton receives the incoming request from the stub and forwards it to the appropriate remote object. It's the skeleton that ensures the remote object gets the message and can act upon it. In modern Java versions, these skeletons are typically generated automatically. This means you, as a developer, don't need to worry about the intricate details of their creation. Instead, you can focus on implementing the functionality of your remote methods. In summary, stubs and skeletons work together, forming a bridge of communication between the client and the remote object. The stub acts as a go-between, sending the client's request to the server. Simultaneously, the skeleton ensures those requests are forwarded to the appropriate remote object. Together, they facilitate seamless communication, making remote method invocation a reality. So, the next time you marvel at the ability to invoke methods on an object residing in a different Java virtual machine, remember the unsung heroes. Stubs and skeletons are the unsung heroes, making the magic of remote method invocation possible. What happens when things go wrong in remote communication? Well, in the world of remote method invocation, we have a mechanism to handle this: remote exceptions. When we're dealing with network communication, there's a whole host of potential errors that could occur. The network could falter, the server might become unavailable, or perhaps the remote object we're trying to invoke is simply not there. To handle these potential pitfalls, all methods in a remote interface must throw a remote exception. This exception is a signal indicating that something has gone awry in the remote communication process. By declaring that a method can throw a remote exception, we're acknowledging the inherent risks of remote communication and preparing ourselves for the possibility of failure. This isn't a sign of defeat, but rather a demonstration of good programming practice. It's about anticipating potential issues and having a plan in place to handle them. Remote exceptions are our safety net, alerting us to problems in the remote communication process. So, what have we learned about remote method invocation today? We've delved into the core concepts of Java's remote method invocation, or RMI, a powerful tool for distributed computing that enables objects in separate Java virtual machines to interact seamlessly. We started by understanding remote objects, the entities that can have their methods invoked from a different JVM. We learned that to become a remote object, a Java object must implement the java.rmi.Remote interface, which signifies its methods can be invoked remotely. Then we moved on to the RMI registry, a server-side naming service that allows clients to locate remote objects by their names. For a remote object to be accessible, it needs to be registered in the RMI registry. We saw an example of how a registry is created on the default RMI port 1099, and how a remote object is registered with the name myRemoteObject. Next, we explored the roles of stubs and skeletons in RMI. The stub acts as a gateway for the client to call remote methods, and it sends the request to the server where the remote object resides. The skeleton, on the other hand, resides on the server side, receives the request from the stub, and forwards it to the remote object. We also discussed remote exceptions, an essential part of RMI. As network communication can be fraught with potential errors, all methods in a remote interface must throw remote exception to indicate they may encounter communication issues. Finally, we touched on the security aspects of RMI. We learned that RMI has built-in security mechanisms, such as SSL/TLS for encrypted communication, and the Java Security Manager for defining security policies for executing code. So there you have it. We've covered the fundamentals of remote method invocation, from understanding how remote objects work to using the RMI registry, to handling stubs, skeletons, and exceptions. We've also touched on the importance of security in RMI. By understanding these fundamentals of RMI, you're now equipped to start creating powerful distributed applications in Java.